Hello students, welcome back to your one and only favorite YouTube channel, Tomachang Tutorial. Myself Kishan Kulum, and today we are ready to go for a new topic in physics, and that is thermal conductivity. Okay, heat conductivity. We have already completed thermal expansion of solid, thermal expansion of liquid, and thermal expansion of gas. So please find the links below in the description and watch those videos. Okay, now let's move on to today's topic. Okay, conduction of heat. Let's read out the definition first and then we will understand. The process by which heat is transferred from the hotter part of a body to its colder part without actual movement of the particles of the body is called conduction of heat. Okay, this is the definition of conduction of heat. It's very simple, but before we understand this definition, let us observe these two cylinders, cylinder A and cylinder B, connected by a pipe. Okay, we can see there is water in the cylinders, isn't it? And we can also see the quantity of water in cylinder A is much more than the quantity of water in cylinder B, isn't it? But the level of water in cylinder B is at higher level than the level of water in cylinder A. Now, if we are asked to guess the direction of flow of water, then we can easily say that the water will flow from cylinder B towards cylinder A, isn't it? This observation concludes that it is not the quantity of water that determines the direction of flow of water. It is the level of water that determines the direction of flow of water, isn't it? Quantity of water is much more in cylinder A than cylinder B, isn't it? Even then, water from cylinder B flow towards cylinder A, isn't it? Now, this is simply because the level of water in cylinder B is at higher level than the level of water in cylinder A. Okay, are you getting me? So, it is not the quantity of water that determines the direction of flow of water. It is the level of water that determines the direction of flow of water. Okay, so the water will continue flow from cylinder B towards cylinder A, okay, until both the cylinders attain equal level. The water will continue flow from cylinder B towards cylinder A until both the cylinders attain equal level. When the level of water in both the cylinders are equal, then the water will cease to flow. The water will no longer flow. The water will become stagnant. The water will become stagnant means the water will stop flowing. Okay, when the level of both the cylinders becomes equal, the water will cease to flow. Are you getting me? I hope you got this. Now let us consider two bodies, okay, in contact with each other, body A and body B, and let us assume the body A has 50 calories of heat energy and body B has only 2 calories of heat energy. Okay, now if the temperature of body B is 80 degrees Celsius and if the temperature of body A is 20 degrees Celsius, okay, we have assumed the heat energy of body A is 50 calories of heat energy and heat energy of body B is 2 calories. 50 calories of heat energy is much more than 2 calories of heat energy, isn't it? But the temperature of body B is 80 degrees Celsius and the temperature of body A is 20 degrees Celsius. Now, if we are asked to guess the direction of flow of heat, then we can simply apply this principle here also. It is not the quantity of heat that determines the direction of flow of heat. It is the temperature. It is the temperature that determines the flow of heat. Okay. Here also the heat energy will flow from body B towards body A because the body B is at higher temperature 80 degrees Celsius than the body B, which is at lower temperature 20 degrees Celsius, isn't it? Now the heat will flow from body B towards body A until both the bodies attain equal temperature. Okay, now since here we can see The difference of temperature is 80 degrees Celsius minus 20 degrees Celsius, isn't it? 80 degrees Celsius minus 20 degrees Celsius is the difference of temperature. So if we subtract, we get 60 degrees Celsius. 60 degrees Celsius is the difference of temperature. Now, when both of these two bodies attain equal temperature, let us say 30 degrees Celsius. This is just an example, okay? I'm just assuming both of these bodies attain 30 degrees Celsius temperature after the flow of heat from body B to body A, okay? Now, if we calculate the difference of temperature, this becomes 30 minus 30, 0 degrees Celsius, isn't it? When the difference of temperature is 0, the heat will cease to flow. Means when these two bodies attain equal temperature, the heat will cease to flow. The same principle of flow of water is applied here also. Okay, got my point? Now, the question arises, heat, we understood that heat flows from hotter part of the body to colder part until the temperature in both parts becomes equal, isn't it? Now the question arises, how does heat flows, isn't it? How does heat propagates, or how does heat travels within the body, isn't it? That is the question which pops up in your mind, isn't it? Now to understand this, let us assume 5 students or the 5 boys are standing in a single line very close to each other, okay? First boy, and just right behind him is the second boy, and behind the second boy is the third boy, and the fourth boy, and the fifth boy, okay? 5 boys are standing very close to each other in a single straight line. Are you getting me? Yes. Okay. Now, if I apply some amount of force and push the first boy, what happens? The first boy will lean backward, isn't it? And collide with the second boy. The second boy in turn will lean backward and collide with the third boy. And the third boy will lean backward and collide with the fourth boy, okay? It goes on, isn't it? Now, what I want you to understand from this is, the boy does not change their places, does not change their positions. The first boy is in his position. The second boy also is in his position. The third boy also is in his position, okay? The boys do not change their position, but only the energy is transferred from first boy to the fifth boy by the collision, isn't it? The energy is transferred from first to second, and second to third, and third to fourth, and fourth to fifth, simply by collision, isn't it? Are you getting my point? So the same principle is applied for the flow of heat. Okay, we know that, let us assume this is a metallic rod, okay? This is a metallic rod. Now we know that every metal is a solid, and solid is also composed of molecules. Are you getting me? Solid is composed of molecules, and these molecules in solid are very tightly packed. Are you getting me? Molecules in solid are very tightly packed, okay? Now, if you hit, suppose this solid is at room temperature before, let us assume 20 degrees Celsius. This solid was at 20 degrees Celsius before heating, okay? Now, when you hit this solid, what happens? We know that solid expands on heating, isn't it? If you have not watched that video, please find the link below in the description and watch the expansion of solid, okay? So, if you hit the solid, what happens? The solid expands in volume, isn't it? The solid expands. And these molecules get a space for vibration, okay? These molecules, when heated, starts vibrating, isn't it? When you hit the solid, the molecules inside the solid starts vibrating. The particles inside the solid starts vibrating, okay? When this particle starts vibrating, it collides with the second particle, collides with the third particle, isn't it? The collision starts. The collision of the particles within the metal starts, okay? And this particle will collide with this, and this particle will collide with this, and all the particles in this area will collide with the next particles to them, isn't it? Similarly, the collision will begin, as you have understood. In case of boys standing in a line, the collision will begin, and finally the heat energy reaches here in this part also. Are you getting me? Are you getting me? Yes. The particles vibrates and collide with the next particle, and the next particle starts vibrating, and that particle collides with the next particle, and that next particle starts vibrating, and that particle collides with the next particle. And similarly, heat energy is transferred from this part of the body to this part of the body. Okay, from this part of the body to this part of the body. Let us say A and B. Okay, the heat energy from part A is transferred to the part B. In this case also, the particles do not move from part A to part B. The particles do not carry heat energy like this and move from part A to part B. Okay, the particles will remain in their positions, in the places. They will simply vibrate in their position. Only the energy is transferred from this part of the body to this part. I hope you got this. So let us come to the definition. The process by which heat is transferred from hotter part of the body, okay, from hotter part of the body means the part of the body which is at higher temperature, because when you heat the body, the temperature rises, suppose 50 degrees Celsius, okay, the temperature of this part of the body is 50 degrees Celsius and temperature of this part of the body is 20 degrees Celsius. There is a difference of temperature, isn't it? This temperature is higher than this temperature, so heat will obviously flow from this part of the body to this part of the body. But how? From hotter part of the body to its colder part, without the actual movement of the particles of the body, okay, without the actual movements of the particles of the body. Particles do not carry heat energy and move from this part of the body to this part of the body. It is not like that. One single particle do not carry heat energy and move from one part of the body to another part of the body. The particles vibrate in their places and collide with the next particle. The next particle in turn starts vibrating and will collide with the next particle. And like this, the heat energy will propagate from part A of this body to part B. Okay, from hotter part of this body to its colder part. I hope you got this. Now we have understood the definition. This is called the conduction of heat. Okay. Now we understood the conduction of heat. Now the question arises, do all substances conduct heat? Okay, now the substances which conduct heat or which allows heat to pass through them are called conductors. Okay, conductors. Conductors means conductors of heat. You can say conductors of heat. Conductors of heat means substances which allows heat energy to pass through them. Okay, the substances which allows heat energy to pass through them are called conductors of heat. And next is non-conductors of heat, isn't it? Non-conductors of heat. Non-conductors of heat. Non-conductors of heat is very simple. The substances which do not allow heat energy to pass through them are called non-conductors of heat. Okay, non-conductors of heat means the substances which do not allow heat energy to pass through them, because they do not expand so much on heating like metals. Metals are generally conductors of heat. Okay, metals are conductors of heat. Metals are good conductors of heat. Okay, conductors of heat. Metals allow heat to pass through them, so metals are good conductors of heat, and non-metals are bad conductors of heat. Non-metals are bad conductors of heat. Bad conductors of heat. Metals allow heat to pass through them, so they are called good conductors of heat, and non-metals are bad conductors of heat because they do not allow heat to pass through them. So I hope you understood this. Now, do all metals conduct heat equally? The question arises in our mind, isn't it? Do all metals conduct heat equally? The answer is very big no. No. All metals do not conduct heat equally. Different metal conducts heat differently. Different metals conduct heat differently. Okay? Differently. All metals do not conduct heat equally, but different metals conduct heat differently. This can be understood from an experiment. This experiment was, designed by Ingenhousz experiment. This is called Ingenhousz experiment. Ingenhousz performed an experiment to prove that different metals conduct heat differently. Okay. Now, what he did in this experiment is, you can see a cylinder, and there are 4 metals. Okay, 1, 2, 3, 4 metals. 4 metals of equal length and equal cross-sectional area, means equal thickness. Okay, 4 metals of equal length and equal cross-sectional area is inserted into the cylinder through a hole fitted with a cork. Okay, so that no liquid from inside may come out. The cork will prevent the flow of heat from inside of the cylinder to out. Okay, these metals are inserted into the cylinder through a hole fitted with a cork. Okay, and these metals are of equal length and equal cross section. Please remember, these metals are of equal length and equal cross section. Okay, now he coated these metals with wax. Okay, he coated these metals with wax. He coated these metals uniformly with wax. Okay, now what he did is, he put some hot water here. Hot water, very hot water. Hot water, boiling water, you can say boiling water. The temperature of this water is 100 degrees Celsius. Okay, the temperature of this water is 100 degrees Celsius. Now, after some time, let us say after 5 minutes, he observed that the aluminum, this is aluminum, isn't it? It was also coated with wax. Copper was also coated with wax. Iron was also coated with wax. Lead was also coated with wax. Now, he observed that in the metal aluminum, the wax melted to the farthest distance. Okay, and copper a little shorter than aluminum, and in case of iron, even shorter than copper, and in case of lead, very short. From this, what we can conclude is, the metal which conducts heat very efficiently, or which is very good conductor of heat, or we can say which allows more amount of heat energy to pass through that metal, is called very good conductor of heat, isn't it? So aluminum allowed so much of heat energy to pass through it that the wax is melted to this much distance, isn't it? Now, copper allowed a little less amount of heat to pass through it, so the wax melted to this much. And this iron allowed a little lesser than copper, so that the wax melted to this much level, isn't it? And lead to this much level. From this experiment, we can be very sure, or we can understand that different metals conduct heat differently. If all of these metals would have conducted heat equally, then the wax would have melted to equal distances, isn't it? The wax would have melted to equal distances in all of these 4 cases, isn't it? Now, the wax has melted to different distances in different cases. This means that different substances conduct heat differently for equal amount of heat or equal rise of temperature. The temperature is 100 degrees Celsius for all of these metals, and heat energy is also equal for all of these metals, but the wax is melted to this distance. Means in aluminium the wax is melted to the farthest distance, means aluminium is more good conductor than copper, and copper is more good conductor than iron, and iron is more good conductor of heat than lead. I am talking about heat, okay, not electricity. Okay, now I hope you got this. Okay, now let's move on to the next topic, and that is dependence of heat current and temperature difference, length and cross-sectional area. Okay, I have already drawn a conducting material, a conducting block. Okay, this is a cuboid having cross-sectional area. Let us say the cross-sectional area is A. Okay, I am assuming the cross-sectional area of this cuboid be A. This area, cross-sectional area is this area. This area is A. This area is A. Okay, cross-sectional area is A, and length of this conducting material, let us suppose x centimeter. Okay, length of this cross-sectional length of this conducting material is x centimeter, cross-sectional area is A square centimeter. Okay, now suppose this surface of the material is the hotter surface. Okay, let the temperature be theta 2 degrees Celsius, and this surface is colder surface, let the temperature be theta 1 degrees Celsius. Are you getting me? This is the hotter surface, and this is the colder surface, and since you know that heat energy flows from hotter surface to the colder surface, isn't it? Heat energy flows from hotter surface to the colder surface. So let us say Q is the amount of energy that is flowing from hotter surface to the colder surface. Okay, Q is the amount of energy that is flowing from hotter surface to colder surface. Are you getting me? Okay, let us consider a conducting material of length x centimeter, cross-sectional area A square centimeter, and temperatures in two phases theta 1 degrees Celsius and theta 2 degrees Celsius. Okay, where theta 2 degrees Celsius is greater than theta 1 degrees Celsius. I hope you got this. Let us consider a conducting material of length x centimeter. The length of the conducting material is x centimeter. Cross-sectional area A square centimeter. This area, cross-sectional area means this area. Okay, this area, cross-sectional area means this area. A square centimeter, and temperature in two phases with theta 1 and theta 2 degrees Celsius. Theta 1 degrees Celsius and theta 2 degrees Celsius. Temperature in the two phases, where theta 2 is greater than theta 1. Okay, theta 2 degrees Celsius is greater than theta 1 degrees Celsius. So this is hotter surface and this is colder surface. Theta 2 degrees Celsius is higher temperature, theta 1 degrees Celsius is lower temperature. I hope you got this. Now, then, amount of heat flowing. Okay, let us suppose amount of heat is Q. Okay, amount of heat Q flowing through the conductor is, number 1, directly proportional to the temperature difference between the two faces of the conductor. Are you getting me? Directly proportional to the temperature difference between the two faces of the conductor. Okay. Now let us assume theta 2 is suppose 10 degrees Celsius. Okay. And theta 1 degree Celsius is suppose 9 degrees Celsius. I'm just assuming it, okay, to make you understand. Theta 2 is 10 degrees Celsius and theta 1 is 9 degrees Celsius. Now the difference of temperature is 10 minus 9, isn't it? That is 1 degree Celsius. Are you getting me? Now let us assume in the second case, theta 2 is 10 degrees Celsius and theta 1 is 1 degree Celsius. Okay, now the difference of temperature in the second case is 10 minus 1. So this is 9 degrees Celsius, isn't it? I hope you got this. So in this case also the heat will flow because there is difference of temperature 1 degree Celsius. But the amount of heat flowing from the hotter surface to the colder surface is lesser in the first case because the temperature difference is only 1 degree Celsius. And the heat will cease to flow when the temperature difference of 1 degree Celsius is fulfilled, isn't it? When both the surface attains equal temperature, the heat energy will cease to flow, isn't it? So the temperature difference is only 1 degree Celsius. When the temperature difference is maintained equal, when the difference of temperature is made 0, then the heat will cease to flow. But in this case, the temperature difference is 9 degrees Celsius. So to become equal temperature in both the faces of this conductor, 9 degrees Celsius temperature difference should become 0, isn't it? So greater amount of heat needs to flow from hotter surface to the colder surface so that difference of temperature 9 degrees Celsius becomes 0. Are you getting me? So more the temperature difference, more amount of heat will flow. Lesser the temperature difference, less amount of heat will flow. That means directly proportional to temperature difference. Directly proportional means more the temperature difference, more amount of heat will flow. Less the temperature difference means less amount of heat will flow. You got this, isn't it? Okay, now let's move to the next point, and that is directly proportional to the cross-sectional area. Of the conductor. Okay, directly proportional to the cross-sectional area of the conductor, which means this is the cross-sectional area of the conductor, isn't it? This is the cross-sectional area of the conductor. This is the cross-sectional area of the conductor. More the cross-sectional area, more amount of heat will flow. Lesser the cross-sectional area, less amount of heat will flow. More the cross-sectional area, more water will flow. Suppose this is a pipe, okay, of cross-sectional area, suppose A1, and this is another pipe and the cross-sectional area is A2, okay. Now water is flowing from these two pipes. Are you getting me? Water is flowing from these two pipes. So the cross-sectional area of this pipe is more, A1 is very much more than, A1 is much more than A2, isn't it? So more amount of water will flow from A1 than A2. A2 is less as compared to A1. Cross-sectional area of this pipe is lesser as compared to this pipe. So lesser amount of water will flow from this pipe. More the cross-sectional area, more amount of water will flow. Less the cross-sectional area, less amount of water will flow. Similar concept may be applied here. More the cross-sectional area, more amount of heat will flow. Less the cross-sectional area, less amount of heat will flow. Are you getting me? I hope you got this. Now let us move to the next point, that is directly proportional proportional to the time of flow of heat. Okay, directly proportional to the time of flow of heat, which means for more time you allow heat to flow from this hotter surface to the colder surface, more heat energy will flow. Less time you allow heat to flow from hotter surface to colder surface, lesser amount of heat will flow, isn't it? Suppose you have a pipe here, okay, and the water is coming out of this pipe and you are collecting it in the bucket, okay, you are collecting in the bucket. Simple example. For more time you allow the water to flow into this bucket, more amount of water will be collected, isn't it? That is very, very simple. And the lesser time you allow the water to enter the bucket, lesser amount of water will be collected. That is very, very simple, isn't it? Similar concept can be applied in this case also. More time you allow the heat to flow from hotter surface to the colder surface, more heat energy will flow. Less time you allow the heat to flow from hotter surface to colder surface, less amount of heat will flow, isn't it? That is very, very simple. Okay, let's move on to the next point, that is inversely. Okay, now comes the point inversely. I hope you understood this. Inversely proportional to the length of the conductor. Okay, now let me give you an example. Okay, these two are metallic rods. This is just an example. These two are metallic rods of same cross section but different length of but same material. Okay, this is of aluminum, aluminum, and this is also aluminum. Okay, both the conductor are made out of aluminum, both are of same thickness, or I mean to say same cross sectional area. Now let us hit this two metallic rods for same amount of heat and for same time. Okay, for same amount of heat and for same time, what happens? This surface becomes hot and this surface also becomes hot, isn't it? And the heat will start flowing from this hotter surface to the colder surface, and the heat will start from flowing from hotter surface to colder surface in both the cases. Let us assume after 5 minutes, when you touch this surface, how would you feel? And when you touch this surface, how would you feel? Obviously, this surface becomes more hotter than this surface, isn't it? So, lesser the length, more amount of heat will flow. Longer the length, less amount of heat will flow. Are you getting me? More the length of the conductor, lesser amount of heat will flow. Less the length of the conductor, more amount of heat will flow. I hope you got this. More the length of the conductor, less amount of heat will flow. Less the length of the conductor, more amount of heat will flow. That is inversely proportional to length of the conductor. When you increase the length of the conductor, amount of heat flowing through the conductor decreases. When you decrease the length of the conductor, amount of heat flowing through the conductor increases. Okay, I hope you got this. Now let us deduce this. Let me erase this, the upper part. Please take the screenshot. I'm erasing it. Okay, and deduce the relation. So from these two 4 points, we can write Q. You know, Q is the amount of heat, isn't it? Q is the amount of heat flowing through a conductor. Q is directly proportional to temperature difference between the two phases. Temperature difference means θ2 is higher temperature, θ1 is at lower temperature, means θ2 minus θ1 is the temperature difference, isn't it? Q is directly proportional to temperature difference, θ2 minus θ1. Are you getting me? Temperature difference. Q is directly proportional to temperature difference. And number 2, directly proportional to cross-sectional area, isn't it? So directly proportional to cross-sectional area A. And number 3, directly proportional to the time of flow of current. So directly proportional to the time of flow of current, T. And inversely proportional to the length of the conductor. So inversely proportional to the length of the conductor, that is L. Let us suppose L, okay, length of the conductor. Inversely means comes to the denominator, directly means remains in the numerator, isn't it? Q is directly proportional to the temperature difference, cross-sectional area of the conductor, and time of flow of current, heat. And Q is inversely proportional to length of the conductor. So, or Q equal to, we replace the sign of variation with sign of equal to sign and introduce a constant K here, okay? Q equal to K theta 2 minus theta 1 into A into T upon L, okay? This K is called coefficient of thermal conductivity, okay? This K is called, here we have written as this K is variation constant, isn't it? K is variation constant, where K is called coefficient of thermal conductivity. K is called coefficient of thermal conductivity. I hope you are getting me. Now, let us find the value of K. Okay. Or K equal to Q into L, isn't it? Q into L, we cross multiply this, divided by theta 2 minus theta 1 into A means L square, isn't it? Area means length square into time. This is the value of K, okay? The value of K depends upon amount of heat flowing through the conductor, length of the conductor, length can be cancelled, okay? Length can be cancelled, so now comes another relation, or K equal to Q divided by theta 2 minus theta 1 into L into T. There was 2L here, 1L and 1L cancelled. So K depends upon the value of K equals to quantity of heat flowing through the conductor divided by temperature difference into length of the conductor into time of flow of heat flow through the conductor. This is the value of K, and the value of K depends upon the nature of the material, conducting material, okay? Value of K depends upon the nature of conducting material, so K is called coefficient of thermal conductivity. Okay, now thermal conductivity. The coefficient of thermal conductivity of a material is defined as the quantity of heat that conducts for unit time through a unit cube of the material when its opposite faces are kept at temperature difference of 1 degree, okay? Let us understand this definition. So we have a unit cube. Unit cube means length, breadth and height of this cube is 1, okay? Let us suppose length, breadth and height of this cube is 1, and this is the one surface and this is the other surface, okay? I hope you are getting me. And the temperature of this surface is theta 2, temperature of the surface is theta 1, so temperature difference is also 1 degree Celsius. I am writing in Celsius unit, okay? Temperature difference of 1 degree, isn't it? Temperature difference 1 degree Celsius. I am writing degree Celsius in Celsius unit. Okay, since length and breadth and height of this cube is equal, so let us write length equal to 1 centimeter and area of cross section becomes 1 centimeter square, isn't it? Are you getting me? So Q amount of heat is to pass from hotter surface to colder surface, hotter surface of this cube to colder surface, and temperature difference is 1 degree Celsius. Length, breadth and height are equal, that is 1 centimeter. So area is length into breadth is 1 centimeter into 1 centimeter is 1 centimeter square. I hope you got this. Now since we know that, we have already seen Q equal to K into theta 2 minus theta 1 into area of cross section into time of flow of heat divided by length of the conductor, isn't it? This was the relation we have already deduced. Okay, now this K is called variation constant, but in this case K is called coefficient of thermal conductivity. Okay, coefficient of thermal conductivity. K is called coefficient of thermal conductivity, and this K, the value of K depends upon the nature of the material. Okay, like aluminium has different K, copper has different K. The value of K depends upon the nature of the material, conducting material. Now let us deduce the unit of K. Okay, K equal to, let us cross multiply, Q into L is QL, isn't it? QL. K equal to Q into L is QL divided by theta 2 minus theta 1 goes to the denominator. Theta 2 minus theta 1 into A into T, isn't it? I'm just cross multiplying this Q into L, and this all comes to the denominator here. Or K equals to Q, let us suppose, in the definition itself it is given that quantity of heat is the coefficient of conductivity of a material is defined as the quantity of heat that conducts per unit time through a unit cube of the material when its opposite faces are kept at temperature difference of 1 degree. Q equals to the quantity of heat, isn't it? Let us suppose quantity of heat to be 1 calorie. Okay, 1 calorie. Suppose amount of heat flowing from hotter surface theta 2 to the colder surface theta 1 is how much? 1 calorie into length of the conductor is 1 centimeter, isn't it? Divided by theta 2 minus theta 1 is temperature, so unit of temperature is 1 degree Celsius. 1 degree Celsius into cross sectional area is centimeter square into time is second. 1 second, isn't it? Time is 1 second. Let us write 1 second. If the heat is allowed to flow from this hotter surface to this colder surface for 1 second, okay? So unit of K comes like this. This centimeter square and this centimeter gets cancelled. Now calories remain in the numerator. Second, when you bring to the numerator, becomes second to the power minus 1, and this degree Celsius, okay, centimeter when we bring to the numerator becomes centimeter to the power minus 1, degree Celsius when we bring to the numerator becomes degree Celsius to the power minus 1. This is the CGS unit of K, okay? CGS unit of K. Calorie per second per centimeter per degree Celsius. Now SI unit of thermal conductivity, SI unit of thermal conductivity of heat, that is K. K is the thermal conductivity of heat, isn't it? SI unit is calorie becomes joule, second remains second, centimeter becomes meter, and degree Celsius becomes Kelvin. Joule per second per meter per Kelvin. Joule per second can be written as work per meter per Kelvin. This is the unit of K, okay? unit of K. SI unit of K can be this or this. I hope you got this. Thank you so much for watching this video and stay connected. I'll upload more videos like this, so please don't forget to subscribe and click the bell icon for notifications. Okay, thank you.